everyone. I hope you're doing well and having a good week. Welcome to the second portion of Module 4. So this module is all about kind of the theories of stuttering. So in the first module, or first portion of the module, you learned about the historical theories from Dr. Hudak, and now this portion of the module we'll be going over the neurophysiological differences found in people who stutter and kind of how that contributes to our body of knowledge about what we think about stuttering. So just kind of an overview. Everything I'm going to present today is very, it's a lot of information and it gets a little bit dense, but I'm trying to keep it as superficial as is necessary for you guys. So you guys need to know a little bit more about maybe the neuro stuttering than like the average person, but you don't need to know as much as like someone who's spending their whole life researching this. And so if you're interested, there's lots of citations throughout this PowerPoint and in the materials that you can look into more. But I'm going to try to give you as clinically applicable information as possible. But just kind of an overview of stuttering from like a neuroscientific level. We know that there are neurophysiological differences in the brains of people who stutter. There's a lot of conflicting research about this, which we'll go over more. But there are studies that have found differences in the areas of emotional regulation and processing, motor control, sensory motor control, attentional networks, as well as kind of the intersection of these processes. And so we're going to go more into depth on all of those things throughout this lecture. So to start off with emotional processing, we know that stuttering is not caused by anxiety or emotions or things like that, but there is an impact of emotion on speech production. Therefore, it's relevant for us to talk about emotional processing because it does impact stuttering. So if we think of emotional processing in general, essentially how it works is first you perceive an emotional stimulus. So something happens that kind of triggers you to have an emotional response. And so what happens next is you have to process that emotion. And the outcome of that processing is there's a physiological or physical response. So like essentially arousal and a lower order response. And then there's a conscious feeling higher order response. So breaking down these two responses, the physical response, that lower order thing, is your lower order system. Essentially, like there's a sensory response, and then that sends signals to the thalamus, the amygdala, the brainstem, and the hypothalamus, which the amygdala, as you guys may or may not know, is involved in autonomic arousal, hormonal secretion, fear, and specifically within that fear conditioning is really responsible for like the freezing and the avoidance reaction to fear response. And so if the amygdala is being activated, then you kind of have that arousal response. The amygdala is really interesting. Researchers could probably spend their whole lives researching the amygdala, but just kind of generally we think of like there's two big things that the different nuclei of the amygdala do. So there's the emotional learning, which is in the lateral nucleus, and then there's the physiological reactivity, which is in the central nucleus, which is what we're talking when we talk about arousal. And then the hypothalamus is really involved in somatic, visceral, and endocrine responses, whereas the brainstem is involved in simple rhythmic or stereotype movements. And so, you can kind of get the sense that those structures that the sensory receptors send that information to are all kind of those lower order responses. And so you have a kind of visceral reaction. So that's like the first, I guess, step in this emotional processing is you respond viscerally in your body. But then the higher order response is also occurring, and that's a conscious feeling response. A higher order emotional response occurs. And so uh, there, the brain receives and integrates information from the current environment as well as past memories to generate a conscious feeling. And so that kind of integration of what's currently happening that is evoking that emotional response, it doesn't happen in a vacuum, right? So like you're experiencing this phenomenon and naturally your brain is going to recall previous experiences when you've had this. And so in that there's kind of two separate parts of your brains that deal with both of those things. So in the current environment, that kind of sensory response that's happening, that emotional processing that's happening from the environmental stimuli, the thalamus and the amygdala again project to the sensory cortex. And so it doesn't just receive projections, it also projects to the sensory cortex. And then the prefrontal cortex sends signals back to the amygdala with updated information about the environment. So let's take a step back and think about the integration of that lower order response and this higher order current environmental response. So that in that lower order response, you have this emotional stimulus and your brain is responding viscerally. And then those parts of your brain that are responding, the thalamus, the amygdala, all those areas, are then projecting to the sensory cortex as well. And so there's kind of that back and forth already. But then during that process, that kind of like check-in that of those two things that are occurring, the prefrontal cortex, which is that really higher order, like being able to have more cognition about this, not just viscerally react, that is able to kind of observe what's happening and be able to say like, okay, so you are responding to the stimulus in the environment. And then it gives it kind of a judgment of like, is this an accurate emotional response or is this inaccurate? So it kind of gives like a check-in. That prefrontal cortex tells you like, okay, like your, the amygdala, the thalamus, all those visceral reactions, like they don't need to respond as much anymore because the danger is gone. You can then you can back off, or the threat is still here. Like you need to still respond. And so that prefrontal cortex kind of like gives the cognition part of this visceral reaction. And so that's like the current environmental response. But then the past memories, the integration of that is that the amygdala is projecting to the lateral prefrontal cortex, the anterior cingulate cortex, which is very important. We'll talk a lot more about that, and the orbital cortex. So all of these are relevant because they're involved in working memory and executive functions. And so, while this whole dynamic with the current environment and that lower order processing is occurring, that the past memories are contributing information to that response. And so, I think this is like a nice way to think about like, if we think about someone who has PTSD, this past memory response is having a really strong impact, right? So like if you have an external stimulus occur, so let's say you hear a pounding, something pounding or whatever, maybe if you are a war veteran, you associate that with your past memory of like being in war. And so then, that past memory contributes to this response. That prefrontal cortex kind of gets overcome by that memory. And so then it's not as able to kind of differentiate what's dangerous and what's not dangerous. And so past memories do have a contribution here. And that can impact kind of how you're perceiving this emotional response, this sensory experience. I want to talk a second about the ACC, the anterior cingulate cortex because it's super important and it's really interesting because it's really related to speech and stuttering. It's involved in cognition, emotional processing, and motor control, which we'll talk more about later also. But essentially, the ACC signals to the brain that an error has occurred. So with that error detection portion of the ACC's role, what it does is essentially when an error occurs, such as you're making a mistake while speaking or tripping over your words, whatever, it's able to kind of send that signal to your brain to show, there's an error that's been detected, and then you can do something about that. It also is involved in response selection, selective attention, and motor planning. There are some studies that have suggested that the ACC is a specifically unique area that provides an interface between cognition and emotion, which I've already kind of been seeing just how deeply these structures are related to each other. The ACC, the anterior cingulate cortex, is involved in a lot of different things. And it does kind of serve as that interface between the emotional response and this more higher order cognitive response. So it's a very relevant thing to think about with stuttering. So motor control. So let's do an exercise for a second. I want you to get up and walk. Okay? I'll take a second and I'll let you do that. Get up, take a walk around your apartment or house or, backyard, wherever you are right now. Okay? So now that you're back, what was that process like for you? Pretty simple? Not at all. It wasn't simple. Your brain just went through so many different steps to get you to take just a few steps around your apartment. First, you heard me tell you to walk. So your sensory system is already activated because you received that message. And then your motor system, your sensory motor system, integrates that message into your plan for that action. So then you had to decide that you were going to follow my direction. Maybe you didn't, But either way, if you decided to, get up and take a walk, you decided to take that step. So there had to be an intrinsic motivation to do that action. And that motivation also required you to have a motor plan of what your muscles were going to do before you took that step, because you can't do a movement without a motor plan in your brain. And so, not only did you have to decide to do it, but then your brain had to actually prepare to do it. So in addition to all this motor stuff, your sensory system was expecting what your muscles were going to do. So this is kind of related to this, our sensory motor system is doing kind of two things at once, and they're very integrated to each other. We're going to talk more about that later, but just a rough idea is that when you're making a movement, your system is preparing for what that movement's going to be like, so that it can be an efficient movement and it can correct errors if they occur. And so when you go to take that step, your sensory system is then expecting what it's going to experience. And so what it's going to feel if you're walking, maybe what it's going to hear if you're outside, whatever. And so it has an expectation of the sensory experience. And then when you actually go do it, it compares that experience to what it's actually feeling like compared to what it expected to feel. And then if there's errors, it can correct them really, really efficiently. And if there's not, then it continues to perform its action. The expectation is compared to that sensory system. And then those adjustments are made. Maybe you stepped wrong or whatever. You can correct that so that you don't fall down. Maybe you're stepping and you're able to kind of make that online adjustment so that you don't fall down. So it's a really important process that occurs. So even though this seems like a very like simple thing, the actual like taking a step or walking around your apartment had a whole complex series of coordinated muscle movements, which the brain selected based on accuracy and efficiency based on your past experiences of walking. So thinking back to that like memory thing, that like using your past experiences in addition to your current environment, you that's also heavily involved. And so there's just like a lot of things to this process. Um, so some things that are involved in motor control, some specific areas of the brain are the supplementary motor area, which is involved in planning and preparation of movements, which is interesting because, like, again, that sensory system, that sensory motor plan that occurs, there's a lot of things that happen before you even do something. And so that part of your brain that is actually involved in like movement, that of like planning and preparing movements, there's actually electrical activity before the movement even occurs. And so it's a very complex process. The premotor area, which is involved in planning and preparation of the movements as well. And then the premotor area is also linked to mirror neurons, which are neurons in the brain that fire not only when you're performing an action, but when you're watching someone perform an action, which you read about in your chapter. There's a lot of research on it if you're interested, but it's essentially it's really important for like empathy and also sensory motor integration. So it's really important for kind of just like actually doing our movements. Also, the prefrontal cortex is activated, which sends modifying input to this SMA and the PMA, which is supplementary motor area and the premotor area. It also does planning, attention, working memory, decision making, emotional processing. We talked about the prefrontal cortex earlier and how its role in emotional processing to kind of, be able to evaluate what's occurring. ACC, again, is coming up, the anterior cingulate cortex, which is involved in attention, emotional regulation, control, and planning of movements. Again, that ACC is kind of the interface between emotional processing and motor control. And then the primary motor cortex. And so that is essentially how you move, right? So like all of those other things that we just talked about, the SMA, the PMA, prefrontal cortex, ACC, all of those project to the PMC, the primary motor cortex, so that it can generate a very simple movement. So that step that you took at the beginning of this little exercise, there's a lot of things that happen in your brain for you to be able to do that. So, all right. So we talked about emotions. We talked about motor control. So is there an impact on each other? Can emotions affect speech production? Well, let's think about this. If we can, there's essentially two different ways to do it. There's two different circuits that are proposed in your book. This one, More Than Fluency, Amster and Klein. They propose two different circuits that could kind of be integrating those two processes. So there's the survival circuit, which is involved in arousal and motor control, that lower order stuff. And then conscious cognitive circuit, which is mostly the ACC and motor control, so that higher order conscious control circuit. Let's talk about them individually. So first, the survival circuit, the arousal and motor control circuit. So this one is the lower order one, right? So this circuit is really just that arousal portion of it. So, we know that when you're speaking, you end up having increased arousal compared to during non-speaking tasks. There's several of these studies found that conclusion that during their tasks that had speech and non-speech tasks involved in their studies, they found that there was more arousal during speech tasks. And this is for typically fluent speakers. So it's not specific to stuttering. They also found that arousal, in addition to like a verbal task increasing arousal, it also went the other way. And so arousal could affect speech movements in typically fluent speakers, not people who stutter. And so they found that there was more variability in lip movements under autonomic arousal tasks. So it wasn't as stable or consistent in their movements. They also found that autonomic arousal occurred during speech and non-speech tasks in adults and children who stutter, and there wasn't much of a difference between the two. And so essentially, like, all of these studies have shown that, like, arousal is not really that different between people who stutter and people who don't stutter. And so even if it is, it's not a significant enough difference for it to be kind of really, arousal is not really impacting motor control, it seems, so far. Maybe more research will show that's not true, but that's kind of what the conclusion has been drawn from those previous studies. The other circuit is a little more interesting. So this was the higher order one. So this conscious cognitive circuit, which involves the ACC, which is, you know, a really cool area of the brain. And so, you know, kind of reiterating, the ACC is involved in the conscious cognitive circuit as part of emotional processing, right? We talked about that. The ACC has a lot of different roles in emotional, attentional, error detection, behavioral regulation, and motor functions. And so it does a lot of things, and it does a, you know, fairly good job at integrating all these different things in kind of one place. And so, you know, with the ACC kind of being that interface between all these different, you know, processes, it's a viable option for this to kind of be the area that maybe if emotions do impact motor control, this might, like, the ACC might be involved in that because it does kind of integrate those two things. So what the research found is that typically fluent speakers, so people who don't stutter, had greater activation in the ACC during difficult linguistic tasks as well as phonological tasks. And so, you know, when the difficulty increased of these tasks, the ACC activation increased. They also found that there was increased ACC activity when there was inaccurate responses. And so it kind of seems that there was a correlation between ACC activation and actual inaccuracy. So whether it's due to, like, inaccurate information or whether it's due to, like, difficulty of task, I don't think that's very clear. But, like, my guess would be, like, on the difficulty side. Like, this circuit is more, or this area of the brain is more involved in these difficult tasks related to stuttering. So what they found is that adults who stutter had greater ACC activation than in control subjects. Specifically, silent reading and word production impacted ACC activations. There was a lateralization of ACC activity. And there was a greater amplitude of error-related activity in the ACC because it does do that error detection response, right? Remember? However, what they found is that this amplitude of error detection in the ACC was actually not correlated with accurate responses or inaccurate responses. So they still found increased ACC activation even when the responses were actually accurate. And so, you know, potentially the suggestion here is that it was detecting an error when there wasn't one. With children who stutter, they also found differences in the ACC, but with kids who stutter, typically the studies are just a lot less focal. Like, it's not as obvious what the differences are. And the study was kind of similar. But this Chang et al. 2017 was a really interesting study because they did find that there were differences in children who stutter, which is not always the case not all studies have found that. But what they found, there were widespread differences in the default mode network, which, you know, is really complicated, but you can read Chang et al. 2017 to, like, learn more about that. But one of the areas in the brain that's interesting here is the ACC is involved in that default mode network. And so it was one of many areas that were impacted that had differences in children who stutter versus children who don't stutter. Okay, so next, like, let's, like, be practical here. Like, this is all interesting and all, but, like, do we care? Like, do we care about emotional processing? Also, if we know that maybe there's differences in this, or maybe this conscious control circuit can impact speech motor control, if that's what we conclude, can working on emotional processing improve fluency? Like, that's kind of what the conclusion you would draw, right? Is if there is an impact that this emotional conscious control network or pathway, circuit, whatever, has on motor control, and motor control is related to fluency, can reducing like emotional reactivity or improving emotional processing improve fluency? Right? That's a very natural question to ask. So let's talk about each of those two different circuits. So survival circuit, unsurprisingly, probably not, right? Like there weren't really differences in arousal. So there's probably not much you can do with that. The other circuit, though, because there were differences in the conscious control or conscious cognitive circuit, and specifically in the ACC, that might actually be true. We might actually be able to impact motor control, e.g., fluency, by working on emotions, which is another reason that you should make sure that you address the below the surface part of the iceberg, that emotional reactivity, the emotional impact of stuttering. In addition to like improving someone's life, it can also maybe increase their fluency, right? So like I think it's dangerous if we promise those things, but given kind of we talked about the emotional processing, it actually may be able to be impacted, which is interesting. And so some studies that have supported that are Choi et al. 2016. They found that working on the cognitive aspects of emotion had a bigger impact than just the arousal aspects, which makes sense with that. Just working the survival circuit probably doesn't do anything. But a lot of the therapies that we do with people who stutter on the counseling side of stuttering therapy, Acceptance of Commitment Therapy Act, and CBT, cognitive behavioral therapy, they address this conscious control circuit, conscious cognitive circuit. And so we're really taking advantage of the impact that the emotional processing can have on motor control by utilizing those therapies. And so more reason for you to be doing counseling in your speech therapy work. So is emotional processing the cause of motor control and stuttering? That's kind of the next question you might ask. The short answer is no, right? Like emotions don't cause stuttering, right? We know that. But emotional processing does impact motor control, especially the conscious cognitive circuit. And so in everyone, like that emotional processing impacts that conscious, the emotional processing through the conscious cognitive circuit impacts motor control. And so it makes talking harder. So in people who stutter, where talking is already hard, you're going to see a bigger difference, right? But it's not specific to people who stutter. Maybe more extreme though. No. So the answer is no, but there are ways that we can improve it regardless of that answer. The other areas that are impacted people who stutter are not just emotional processing. So there's attentional aspects of our executive functions, which includes the ACC. There is hemispheric lateralization. So this is something I think you talked about in your other video. There was a theory proposed by Orden in 1927 that was called the cerebral dominance theory, which was kind of just when the field started moving into this idea that like stuttering has neurophysiological differences, and tried to understand what they were. And so back then, the 1920s, we didn't know how to research this. And so there was a lot of work surrounding the high kind of like left-handedness is bad movement that was occurring at that time. And so what they found is that studies kind of started showing that people who stutter tended to be left-handed. There was some promising studies that found that there was a higher correlation um, with people who stutter and being left-handed, but the results were kind of inconsistent. And so it wasn't, a perfect hypothesis, but there's something they started to notice that like maybe people who stutter used the opposite side of their brain for speaking. Maybe it wasn't because parents did something wrong, like it's kind of shifting from that idea. Um, so to kind of make this a little bit more sophisticated as our technology got a little bit better, and as they realized like the left-handedness wasn't the perfect answer, they switched to left-sidedness. And so they researched this a lot in like dichotic listening tasks. So essentially they were looking to see where the ear advantage was. So there's a left ear advantage or a left ear advantage or a right ear advantage. And what the typically fluent person does is there is a left ear advantage for linguistic tasks, linguistic stimuli, and then a right ear advantage for melodic tones, like the musical stuff. And so what made them interested in this is that 55% of people in this study from Curry and Gregory in 1969, 55% of people who stutter had a left ear advantage on a verbal task. And that was not what they expected. So I actually mixed it up earlier. So a typically fluent speaker has a right ear advantage because it's contralateral. So they expected a right ear advantage and they found a left ear advantage. Now it wasn't, 100%, but it was much more than the people who don't stutter. But then there's a lot of studies that have tried to duplicate this, and they found pretty inconsistent support. It was just kind of all over the place, whether people who stutter had left ear, right ear advantages, or if it was really deviant from the norm. But kind of this idea that like there were hemispheric differences then led to even more sophisticated technology using EEG, electroencephalography, and ERPs, which is event-related potentials, to support this hemispheric laterality. So what a couple of studies have found is that there is a suppression of right hemisphere alpha waves. And I'll get more into this when we talk about sensory motor differences in a second. But alpha waves are one of two waves, it's alpha and beta waves, that are involved in sensory motor control. And there's been quite a bit of research that kind of suggests that people who stutter have sensory motor differences in how they process speech and language. And so finding that there was a suppression of right hemisphere alpha waves, which suppression is kind of like activity, if you think about it that way. So like the fact that it was right hemisphere is relevant here. That kind of indicated that there was a more right hemisphere processing of sensory motor control, which is related to speaking. So again, like extrapolating, like that kind of suggests that there's a right hemisphere processing of speech, which is different because usually you see processing in the left hemisphere. There's also a lot of structural and functional differences that people have found. There's a ton of really dense information on this, but essentially what people have found is that there's structural and functional differences in the corpus callosum, in Heschel's gyrus, the left and right superior temporal gyrus, the supplementary motor area, the basal ganglia, the thalamus, the arcuate fasciculus, the longitudinal fasciculus, the inferior frontal gyrus, the premotor cortex, and the motor cortex. Also, typically, the average person, the typically fluent speaker, has left hemisphere asymmetry. So their left hemisphere is specialized for speech and language. It's asymmetric because it's not bilateral. And so the asymmetry is on the left side. However, people who stutter in a lot of these studies have not had this asymmetry. Actually, in fact, there tends to be a lot of right asymmetry. So you see the right hemisphere activated more so than the left hemisphere. Most research suggests that this finding is due to a compensation of stutter rather than kind of like a causal thing. And so because there's some kind of deficit, I guess, in the left hemisphere, our right hemisphere tries to compensate to deal with that. And so there's a right hemisphere overactivity. These structural and functional differences have been found in both state and trait differences. And so state and trait are two different ways of thinking about like, especially neurophysiological differences. So like state differences occur during a specific moment or a specific task. They're not present all the time. And so a state difference in people who stutter might be something that occurs during stuttering or during speaking. So specifically what some of these studies, Poole et al. 1991 and Wu et al. 1995 found is that there were state differences during stuttering, but not during fluency. And then they also found, though, that there were trait differences. So trait differences are kind of what's present all the time. So what these studies looked at is resting state. So during a moment when you're not doing anything, you're not speaking, you're not stuttering, there were still differences in structural and functional. There were structural and functional differences in people who stutter, even at rest. And so those are trait differences. So again, like pretty much everything in all this research, there's inconsistency. The biggest study, I think, probably to not find this was Ingham et al. 1996. They didn't find any functional or anatomical differences related to asymmetry, which was not the norm. So the majority of studies have found differences. However, again, they may not be the product of stuttering. They may be a compensation of stuttering. And so it's impossible for us to know that, but that's kind of what the general consensus is. In addition to these kind of neurophysiological differences, there's studies that have found gray and white matter differences. And so this is in the actual like composition of the brain in the gray and white matter of the brain. And so what they found specifically were that there were gray and white matter differences that were underlying areas related to sensory motor integration, speech timing, dopamine activation, and compensation of, like the right hemisphere is compensating. So that's kind of what the implications of those differences were, the neural structures that they underlie. So some structural and functional differences in children who stutter were not as consistent. So a general research kind of shows that there's a lot of, by the time you reach adulthood, you really see this asymmetry that is atypical. So the right hemisphere is compensating. But then in kids, you don't always see that. You typically actually don't see that. One study, Foundis et al. In 2001, did find this though. So it's not perfect. So there might be a difference in asymmetry. It's kind of yet to be totally understood in kids. What they did find is that there were white matter differences underlying left here, orofacial motor regions. So the motor regions that are responsible for the face and larynx specifically, which is related to talking, right? So like the motor regions that allow you to speak have white matter differences. That's very relevant because you need that to talk, and there's differences there. And so like that could be more of like where you see more breakdown. That is not as much due to compensation, potentially. So some of the differences outside of white matter were that there were gray matter differences in the superior temporal gyrus, STG. Interestingly, what they found is that overall there was decreased left STG activation within the stuttering group as a whole compared to the control. However, within that stuttering group, they found that there was increased left and right STG activation in the persistent stuttering group. So kids who continued to stutter had increased left and right STG activations. So it's possible that they're needing to kind of compensate more because they are persistent in their stuttering versus kids who don't persist. I think that's a really interesting idea because even those kids who did persist still had overall decreased left STG activations than compared to the control group. And so there were still differences, but like within those two persistent and recovered kids who stutter, there were differences neurally. And so I think this is a really important thing to think about because more and more research kind of shows that there are differences in kids who persist and kids who recover from stuttering. And so that's a very relevant clinical application, especially when we think about like it's possible that like we see a kid for therapy and we do everything we can to help them recover or whatever, and they don't. I mean, it's very possible they were never going to because their brains are just different. And so I think this is an area that really needs to be understood more so that we can know like exactly what we can do with preschoolers and what we can't do, what is just the way their brains work. But within this, there is essentially two different connectivity like loops with kids who stutter. So there's the BGTC, which is the basal ganglia thalamocortical loop, which involves the putamen, the SMA, and the PMC. And then there's the auditory motor network, which involves the pars opercularis and the posterior STG. And so what they found in kids who stutter is that they had greater connectivity in part of the right side of the BGTC, so the basal ganglia cortical or thalamocortical network. But then they did not find that there was left auditory motor network connectivity differences. And so, there were differences even within those circuits. And that's, kind of those differences they found in those kids who stutter. So another thing they keep finding in kids who stutter is that there are rhythm processing deficits with the underlying structures in the brain that are involved in rhythm processing. Those are impacted as well. And so rhythm is really important when it comes to speech production and perception, as well as timing. And so those are things that we start to see, or we see breakdowns in adults who stutter is speech perception, and then timing of speech. And so, when we see these kind of almost like precursor skills, right, like rhythm processing, being in deficit in kids who stutter, that's almost like a underlying skill to some of the other things like speech production, speech perception, timing. And so those are other things that they found in kids who stutter. Okay, so sensory motor differences. So there have been quite a few studies that have looked at specifically what are the sensory motor differences in people who stutter versus people who don't stutter. So what they found is that there are differences in both alpha, which is involved in sensory and motor, and beta, which are involved in motor bands of the frequency bands of the brain. And so with sensory and motor bands being impacted, that illustrates that there's sensory motor impacts on the brain. And sensory motor integration is very involved in speaking. And so in order to kind of think about this, there have been studies like the ones listed here that have found these differences in these bands. But to think about how that impacts other structures, because all of these other studies that have looked at these sensory motor differences have only been able to look at kind of surface structures. So like if you're looking at alpha and beta bands, you're looking at the premotor cortex mostly, because that's where the sensory motor areas are like mostly involved, and they're pretty surface level structures. So we can't see things like the basal ganglia and the parts of those networks that are connected in the brain, you can't get at those deeper parts of the brain because you can't see them with like something like EEG technology. And so what this DIVA model, the directions into velocities of articulators by Gunther 2008 did, is they used computational modeling to kind of think about how deficits in these areas that research is finding, how that contributes to the different theories of like the cause of stuttering. And so essentially they came up with two different theories. There's the WMF theory, which is the white matter fibers theory, and then there's the dopamine theory. And so in the WMF theory, they looked at research that found differences in the left precentral gyrus, and they tested to see what would like disturbances in certain areas, how that would impact speech production. And so they did that for actually both circuits. And so in Severe et al. 2013, they used the DIVA model to test projections to see if they would lead to stuttering-like disturbances in speech production. And so with the WMF theory, they thought that corticostriatal white matter fibers from the ventral premotor cortex to the brainstem projections led to stuttering. And so the research from the left precentral gyrus contributed to this idea. And so what they thought is that circuit between the left ventral premotor cortex and the brainstem was the impacts of that circuit would lead to stuttering-like dissonances. And so that part of the theory, or that theory, would contribute to mostly medial and final utterance dissonances and not as much other parts, but that like most closely would align to that. The dopamine theory was that they proposed that elevated dopamine levels in the putamen would lead to stuttering. And so that would account more for the initial utterance dissonances and not as much the other parts of the word. Both they suggest would account for most types of stuttering, but like those parts of the utterance would be most easily accounted for with these different theories. So what they found in this study, this computational modeling, was that the simulation supported both theories. Both conditions could prevent the function of syllable sequencing circuits, which consisted of the basal ganglia, the thalamus, and the left ventral premotor cortex. And so essentially those neural anomalies would lead to delays in the movement of the next syllable. So if you have that delay in the current syllable and the projection to the next syllable, the motor plan to the next syllable, you would have breakdowns, which would kind of present as stuttering-like dissonances. So that is kind of what the DIVA model was used to understand these sensory motor differences. So just a very like brief background on like sensory motor integration, because it's I think very heady. It gets very confusing. So and with the DIVA model, I think it's important for us to think about kind of how we think this model is supposed to work, and then we can kind of start to understand the breakdowns. And so sensory motor integration is necessary for speech. It's necessary for most things, for most movements. So let's imagine you're going to pick up a glass. Let's say you go to Chili's, okay? You go to the restaurant called Chili's and you go to pick up a glass. So when you go to pick that up, you have your past knowledge of what that experience is going to be like. You have, and your sensory system is expecting for you to feel a certain way for a certain, you know, I guess in this case it's mostly to feel a certain way. Additionally, your motor system is expecting to exert a certain amount of energy, a certain amount of force to pick up the glass. And so that expectation is the feed forward control system. And so essentially, you have an expectation of what you're going to, so that's the speech sound map here. So again, we're not talking about speech right now. We're talking about like a non-speech example, but it can be applied the same way. And so you have, a speech sound map, and then you have like this expectation. So the articulator, velocity, and position maps. So you have an expectation, which leads to initiation. And so once you have that expectation of what is going to occur, then you perform your action. So you go to pick up your glass. So let's say you pick it up and it's the right amount of weight. It feels the way you expect. Then there's not really anything to correct. And so, your system then takes the somatosensory, target, what's occurring in your sensory system. It takes what is hearing, if it's speech, you're hearing something, and it compares them. And then if there's an error generated, so if there's an error in how you're feeling, then it corrects it. If there's an error in what you're hearing, then it corrects it. It does that really quickly because it has a really strong expectation of what it's going to hear, what it's going to feel, etc. If it doesn't, then it just keeps moving and it's really efficient. So let's say, okay, I picked the example of Chili's for a reason. So if you've ever been to Chili's, they have these glasses that look really heavy. They look like they're made of like really thick, like glass. And so you see them and you expect they're going to be heavy. And then you go to pick it up and it's not heavy because they're really light because they're made of like plastic. And so when you go to pick it up, if you do not adjust your motor plan, if you don't change how much force you're going to pick your glass up, then when you bring the glass to your mouth, you're going to hit your face because it's going to be too fast, too hard, too fast. And so this system works by correcting that before you hit your face. And so it notices, oh, this is really light. This is like not what I expected. And that error signal is generated from the ACC. And it tells your brain like, hey, you got to correct your motor movement. And so the brain does that really quickly and it corrects that motor movement. So then you can slow down your movements. You don't have to put up much pressure. And then it's appropriate for the stimulus, for the like glass. So that's like essentially how the system works. With speaking, it's the same thing. You go to talk, you expect to hear something, you expect to feel something in your mouth, whatever. And if that is accurate, it keeps moving. It makes a comparison, it keeps moving. If it's inaccurate, an error is detected, and then it corrects that error. With people who stutter, this doesn't work very well. Something about it doesn't work very well. Max et al. 2004 thought that there was an unstable feed forward plan. And so essentially the expectation wasn't very accurate. And there was an over reliance on feedback. And so it was very inefficient and it was a little bit delayed. So because it was just relying on online monitoring of what your speech sounds like and feels like, and it didn't have these feed forward projections to kind of help keep you moving forward, it constantly made you delay, or it occurs as we talk. It constantly makes you delay to make sure that you're producing your speech and correcting your speech, which that delay results in kind of disfluencies because it's not continuing its movement forward. That's one hypothesis, is that it's unstable, inconsistent. etc. So yeah, that's essentially a brief rundown of sensory motor integration and how it's impacting people who stutter. So, how do we see this clinically? First of all, a lot of the fluency enhancing conditions can be explained, or we can explain the brain of people who stutter through these fluency enhancing conditions and what they're doing to people. And we can also explain how they work through what we understand the brain. And so there's a lot of conditions such as that we know enhance fluency, such as choral speech. All these conditions, not only do they enhance fluency behaviorally, but they also have been found to reverse the hemispheric laterality. So if we think of so much of the studies have found all these different areas of the brain on the left side that are not working as much. They're not as activated. And then the right hemisphere is overcompensating to correct this deficit in the left hemisphere. And so, what these studies or these conditions have found is that right asymmetry gets reversed to the left, which is more what a typically fluent speaker looks like. And so choral speech, which is where two people read in unison with each other, super fluency enhancing. It's like 90 or more percent fluency enhancing for people who stutter. And so it also turns that right asymmetry laterality into left asymmetry laterality. Reading silently as compared to reading aloud does the same thing. Singing, which we know is fluency enhancing, and we also know we use the right side of our brain for that. But it's interesting because they did find like a hemispheric reversal in people who stutter. Paced speech and then delayed auditory feedback, which is essentially talking when you hear yourself feedback. So these things are fluency enhancing behaviorally, and they also have impacts on our brain to where we look more like people who don't stutter. It's more typical in how it presents. Okay. So therapy also does the same thing. So there are fluency shaping therapies that have actually found a similar process to occur, that the atypical right asymmetry gets reversed to left hemispheric symmetry. And so they found this in biofeedback. They found this in fluency shaping therapy, where that alpha suppression that was lateralized to the suppression was more in the right hemisphere, which again, suppression is more like activation, right? So like essentially you're using your right side of your brain for that sensory motor control. They found that it was lateralized back to the left hemisphere, which is more expected. Widely distributed laterality becomes reversed. And so that widely distributed left or right hemisphere activity gets reversed back to the left hemisphere, which is more expected. Under a specifically fluency shaping, specific fluency shaping program called precision fluency shaping therapy, they found that directly post-treatment, there was a bilateral symmetry, actually, of the brain. And then post-therapy, so 1 year post-therapy, it actually had turned from right lateralized to bilateral to left lateralized. So a year after, the brains of people who went through this therapy actually looked more like people who don't stutter. And then they also found an increased activation in frontal and temporal regions bilaterally, with notable differences in the left, which frontal and temporal regions are very involved in speech. And then they found a normalization of planning and execution of speech and the basal ganglia. I think it's super important for us to talk about the good and the bad of this, right? So like, this sounds awesome, right? Like these fluency shaping therapies are changing the way your brain is structured, and they're making you look more like someone who doesn't stutter. So the big thing to be aware of is that these therapies, even when they lateralize your activity, even when your brain looks like someone who doesn't stutter, you still talk really weird. So even though like your brain is looking like someone who doesn't stutter, you don't sound like someone who doesn't stutter. And so in order for you to achieve that laterality that is like a fluent speaker, you have to change the way you're talking so extremely. So it's very contrived, right? That's what it feels like to me. Of like you're actually changing your brain like activations because of how differently you're talking. So I think this is an important thing to remember because, you know, I think from a neuroscience level, it seems great, but from like a practical level, like it's not these therapies that change the way you talk so completely and they require so much conscious effort and they make your speech sound so odd. Specifically this one, like the precision fluency shaping therapy, most fluency shaping therapies, they make your speech sound so odd that it's not worth like the way that your brain looks different. Like no one knows that, right? Like, and so there's a disconnect between the neural level and the behavioral level. But interesting, right? Like, I think that there are clinical relevances that are more manageable. So I should have mentioned this earlier, but thinking about this sensory motor integration, if there's an unstable plan, if you have an unstable feed forward plan, and you rely on feedback too much, and you kind of studying your results because of this delay of like having to rely on feedback, and it's just delayed and it's not as efficient. One thing that kind of I guess accounts for that delay, it takes advantage of the stable sensory, the stable feed forward plan is a vowel prolongation. So if you're talking in prolongations, that stable vowel prolongation is a very stable plan. And so it's kind of stabilizing a very unstable sensory motor system. And so, you know, there are things that we can use the neuroscience to apply clinically and practically. So, you know, we don't recommend precision fluency shaping therapy. We don't recommend fluency shaping therapies, you know, broadly in general because the benefits don't outweigh the cost. But, you know, we can use this neuroscience stuff to understand maybe what treatments are more helpful and which ones are not. I think of some of the research that I did in my master's, found just, I looked at like the differences in different fluency enhancing conditions, like choral speech, delayed auditory feedback, prolongations, and pseudo stuttering actually, and looked at how those conditions impacted sensory motor systems of people who don't stutter. So it's not people who stutter. That would be the next study to do. But you know, being able to understand which of those conditions had a greater impact in the sensory motor system allows us to understand, you know, how we can use them clinically. And they kind of fell in line with what this research found was that, you know, those conditions did increase, like they changed the way the sensory motor system processed those conditions compared to the control conditions, which with people who stutter, if your sensory motor system or your system in general is atypical, you know, lateralizing it to be more typical is usually related to a behavioral fluency increase. So that's a helpful product. So why do the fluency enhancing conditions work? I kind of alluded to this, but there's a couple of ideas. So one is that it's just a conscious attention that, you know, if we think of that, there's not just one of these neural systems that is impacted. There's attentional impacts, there's emotional impacts, there's motor control, there's sensory motor control, you know, all these things. The conscious attention that is exerted on talking when you're doing like a therapy, that might be a point of alignment, especially if we think of like the ACC, the MVP of all the brain structures. It kind of brings together all of those systems. And so, including the attentional control. And so that just having more attention on how you're speaking might actually be the element of this therapy that is enhancing our fluency, and changing these neural structures. And then it might just be that changes in sensory motor control from therapy. And so if you're talking differently, it changes how you're hearing your speech. It changes how you're producing your speech, which also is that conscious attention, but also your motor plan is different. That results in changing sensory motor control, which we know that there's a lot of conditions that change the way we hear our speech and the way we feel our speech, the way we process or produce speech, that are fluency enhancing. And so it very well may be that the expectation of our sensory system is not what we're expecting, and so it might result in fluency because it's different from what our expectation is. And then also, again, as I mentioned with prolongations, when you're producing a vowel, the vowel is a very stable production on an acoustic level, and it's slowing down the speech production system. And so it's allowing that time for that delay for that unstable system to stabilize. And so those are just some ideas as to how these conditions and these therapies impact our neural systems and induce fluency. So that is a very wide overview of what we think about stuttering at the neural level. If you have more things you want to learn about this, check out the citations I put in here. The articles that you're reading for this week are really helpful. But essentially, learn what you need to know about this stuff for your clients. It's important for people who stutter to know that it's not their fault and that there's something about our brains that works differently. It's not related to intelligence or anything like that. Our system works well in lots of ways, but the way that our brain processes speech is different on many levels. And so I think just having that knowledge to give to your clients is helpful, because then it takes the shame, the guilt, the weight off of them. And so, if that's all you take away from this, then I think that's still really helpful. So, best of luck with this week, and I'll see you all next time.